Simple harmonic motion. A special type of motion when a particle moves in a straight line is called simple harmonic motion. That's a particular type of motion that we're interested in. If the displacement of the particle is x is equal to a sine nt plus k, then the velocity of the particle is, just differentiate this and we can see this n comes out here as a factor. So we have an cos nt plus k, and then the acceleration is negative an squared sine nt plus k. Again, just differentiate using the chain rule. The acceleration is related to the displacement, as we can see from above. If we just have a look here, this has a, and it has the sine nt plus k, just like this. So the difference between the a and the x is the negative and the n squared. So we can say that a is negative n squared x. This equation informs us that in this type of motion the acceleration is proportional to the displacement from some fixed point and is directed towards that point. And really importantly, if you're asked to prove a motion is simple harmonic, if you can get this expression, it proves it. Get that expression from a given displacement. The greater the displacement from that point, the greater the acceleration back towards the point. We can see that as x increases, the acceleration is going to increase. Remember, the n would be a constant. Such motion is said to be SHM. If a body moves about a mean position such that x double dot, which is how we often represent a, the second differential of the displacement, is negative n squared x, then it is said to exhibit simple harmonic motion. And we mentioned this before, that by showing this you can actually prove that the motion is simple harmonic. So what does it look like? Basically it goes backwards and forwards on a line. So it just oscillates backwards and forwards between these two endpoints. It will be going fastest at the middle, and at the middle the acceleration clearly would be 0. And then as it goes outwards here, the acceleration is back towards the middle, so it slows down and then it stops at C, then it accelerates back, gets its maximum speed on the way back, and then over here it would accelerate back towards O, so it would slow down until it stopped at B and then accelerate back again. So let's say the particle is here. X is measured positive in this direction, so it would have a positive displacement. To the left of O it will be negative. And let's say it's going this way. In this case the velocity is positive. So the particle here that's moving towards C has a positive displacement and a positive velocity. The acceleration, when it's on this side of O, would be to the left, so the acceleration is negative. The amplitude is the distance from O, which is known as the mean point, to one of the ends. That's the amplitude of the motion. And that's actually equal to A here in this original equation. So P could also be on this side. The displacement's positive, but it could be coming back this way, and then the velocity would be negative, and of course because it's to the right of O, the acceleration is to the left. So this would be a situation where displacement is positive, velocity is negative, acceleration is negative. And then you can just think for yourself, based on what we've said, what would be the situations with the particle on this side. For x is equal to a sine nt plus k, the period of the motion is given by t, that's the period, is 2 pi divided by n. and the amplitude is the magnitude of A. This A could be negative depending on where the particle starts and the direction it's initially going in. So the amplitude is the magnitude of A. If the motion starts in the center O, then if the particle moves to the right initially, x would be equal to a sine nt. The k would be 0 if we start at O. If the particle moves to the left initially, then x is equal to negative a sine t. Essentially what we're saying here is if the motion starts at the center, then k is 0. That's not really too hard to think about. If t is 0, then we need k to be 0 so that sine is 0. If the motion starts at the end, then very often we use cos because it would be nt plus pi by 2, and we know that transformation would give us a cos. If it's from NC, then it's a positive A. If from end B, you need to refer back to the diagram, then it's a negative. So, referring back to the diagram, this is end B, and this one is end C. This is not difficult. At NC, k is pi by 2, and sine of nt plus pi by 2 is the same as cos nt. We mentioned that just now. So let's consider the graph of y equals sine x. So we start when t is 0, x is 0. Then it goes out as t progresses to 1, comes back down to 0, goes to negative 1, comes back to 0, and continues in that way. And that describes our motion backwards and forwards along this line perfectly. So initially t is equal to 0, the displacement is 0, we pointed that out here at the origin. As time progresses, the graph goes up to 1, then down to negative 1, then back up to 1, and so on. So it's a motion that goes backwards and forwards. Consider the graph of y equals cos x. In this case, it starts at 1. So initially t equals 0, the displacement x is 1. And that's why the cos version was for the end of the line. As time progresses, the graph goes down to negative 1, then back up to 1, and so on. So once again, describing the motion along the line, but starting at the end. The period of the graph, t, is given by t is 2 pi over n. We've mentioned this before. The frequency, the number of oscillations per time period, is given by f is 1 over t. So the period is the amount of time to complete one complete oscillation. The frequency is the number of oscillations in a time period, and therefore we can see this inverse relationship. So period is the length of time it takes for the particle to complete one full cycle. So that would be, if we start at the middle, going out to the end, back to the other end, and back to the middle. So that's the period, and frequency is the number of times, the number of cycles it completes in a time unit. So if we had something that had a period of half a second, then it would do that in half a second, and in 1 second it would do that, so the frequency would be 2. Examples of SHM include a mass hanging from a spring, tides, Ferris wheels, etc. The maximum velocity will occur when the particle is in the mean position. This is where the acceleration is 0. We discussed that earlier. The velocity will be 0 at the extremities. We've discussed that. That's where it stops and comes back. And this is where the acceleration is maximum. We know that because we know that the acceleration is equal to negative n squared x. So the acceleration is going to be most when x is at its largest. Consider the velocity at any displacement x. Now in this case we're working with an x is equal to a sine nt plus k. So if we differentiate that, then we know that v is an cos nt plus k. Squaring both sides gives us this, and then use this trigonometric identity. So v squared would be n squared, replace the cos squared here with 1 minus sine squared, and we have a squared minus a squared sine squared nt plus k. But x is equal to a sine nt plus k, so we can replace this with x squared. So v squared is n squared into a squared minus x squared. So v squared is n squared a squared minus x squared. Looking at this equation, we can see that v is equal to 0 when x is positive or negative a, i.e. when the particle is at the extreme ends of the motion, and we know that to be true. We've described that before. We can also see that when x is equal to 0, v is positive or negative n times a. So the maximum velocity is na.